So now we go to the last presentation in the morning that will be given by Francis Albarede, and we are going to geochemistry. Where did geochemists hide during the Plate Tectonics Revolution?
Thank you for being here. You may be wondering what a geochemist is doing here. I'm wondering myself, and I would like to thank the organizing committee for inviting me over. Maybe they looked at their fun book and they mixed up with Claude Allègre, and who could have been here today. There's someone probably more appropriate, but Claude is sick, as a number of you know, and so I'm going to try to, since there is not a single paper that we can consider as a founding paper of plate tectonics due to geochemists. At least this is my assessment. I'm going to try to recreate the atmosphere of geochemistry and petrology at the time plate tectonics was invented. I'm sorry, I will apologize ahead of time for not presenting anything with low temperature geochemistry, but it is not my field, and I'm not sure that it's a wrong thing to do. So if with R in the mind of geochemists in those days, you know, there were some great names. There were some technology was evolving very fast. Harold Urey had convinced Kennedy to launch the Apollo missions, and people were actually on the moon, and it was a big mouthful for geochemists and petrologists. And well, first make you realize that there were days when the technology has actually evolved. I don't know how these guys works, but this is fine. We had major changes in technology, and that's what happened in earth sciences that could be related to petrology and geochemistry is essentially a number of major changes. The first dealing with the trace elements, and I would like to quote the names of Schilling and Winchester. Jean-Guy passed away a few months ago, and electron probe with a big French name was Raymond Castin, who invented the in situ analysis, and Benson Halby, who invented the way to make it quantitative and mass spectrometry. So Jean-Guy Schilling put to work with the help of Michel Trey in many sense, actually developed the concept of trace element analysis, and in particular rare earth elements analysis, which would prove absolutely crucial for the moon, but also for the understanding of the process at mid-ocean ridges. So we got some rock samples irradiating under a very strong flux and actually measured the decay product. And that was something that allowed some very high quality. I would also like to mention Larry Haskin for the similar effort. For the in situ analysis, you've seen these machines. Raymond Castin invented the electron probe in the 50s, actually, but this machine was of essentially no use for 10 years until someone came, and the someone was actually Benson. There were Benson and Alby, who actually made the machine quantitative, and you could produce these beautiful maps here with elements that we all use, or you could make some profiles, and we could understand the nature of the geological processes under the microscope, at the microscopic scale. And probably one of the monster of geochemistry here is Jerry Wasserberg, pouring some liquid nitrogen into this famous lunatic one from the lunatic asylum And you see that actually there was a quantum leap in the precision. I'd like to refer to Dan Mackenzie's statement earlier on today. Papanastasiou and Wasserburg changed entirely the way isotope measurements were made with the help of someone who knew where Vic Nuno and here. And we could start making decent isochrones. We could measure some uranium-lead ages, and because of all the progress, attaching a computer to a well-designed mass spectrometer was something that changed the rules of the game. That was the context. Then we have a number of petrologic or geochemical concepts that came about, and we don't realize that today, that some of the petrology and some of the geochemistry we live with every day is actually something that has been invented, and I'd like to refer you to these things. It was not always something very easy, and people were go right and left and up and down. For those who know, the CAF path is exactly what it is. People were going forward, were going backwards, and there were some strange ideas, okay? And Engel, Al and Celeste Engel at Scripps, in a sense, discovered the original, the perfectly singular nature of mid-ocean-rich basalts. This is not until we could dredge, until we could collect some samples. We would not imagine anything that would look different from Hawaiian samples or from Massif Central or from other places. And by dredging the seafloor, they realized that the ship was actually bringing back something very, very different. And so started a big battle here on the composition of basalts from the mid-Atlantic ridge. And with some famous names, you can see even the greatest names in petrology and geochemistry have not always been right, okay? It's not like in geophysics, of course. And here you have these amazing statements, this seeming dependence on composition upon elevation. It means between morbs and ocean islands, okay? Appears to argue eloquently for the derivation of the elevated alkali basalt come from apparent toluidite magma by gravity differentiation. Oh, sometimes wrong, never in doubt. And this is the same kind of statement by Ringwood, the interrelationship of the three major types of magnetite, quartz tolite, high lumina basalt, and alkali basalt. I explained by magma segregation or fractional crystallization. None of them had actually realized that there was something slightly more complicated than the crust and the mantle, okay? It was slightly more complicated than this. So during much of the 60s, the deep running vision of the mantle as a chemically homogeneous entity was shared by both petrologists and geochemists. So then came a number of events, came the rare earth elements, and this is Fred Fry and Larry Haskin, you know, and here's Larry Haskin, who passed away something like 10 years ago, and discovered that these basalts, either morbs or ocean island basalts, could not be related to each other. I mean, were very different in terms of rare earth elements. But nevertheless, they say that this is a dichotomy of rare earth element distribution, but they still thought that the morph source was a primordial source. They thought that the mid-ocean ridge basalts, which we found at mid-ocean ridges, were actually sampling a primordial mantle. And that's today, it sounds very, very bizarre. And then came the real giant for me, someone who died at the age of 43 and was running the Apollo missions, Paul Gast, and who demonstrated two absolutely major things in earth science today. First, that ocean islands, these are, for those who are familiar with these ocean island basalt, these are rare earth elements. No. What's going on here? And you can see that here you have ocean island basalts. In those days, we used to like to call them alkali basalts, and mid-ocean ridge basalts. First, they could not be derived from each other. So we had two different types of mantle. This was something which is going to be very relevant to plate tectonics. And the second thing is that these basalts, the mid-ocean ridge basalt, had a long history of melt extraction. They were not primitive, because the source, the argument is very long, but believe me, here it's a magnificent paper in 1968 showing that mid-ocean ridge basalt have to come from a mantle, that a used mantle, second-hand mantle. You call it the way you want, but the upper mantle, which produces the mid-ocean ridge basalt, was a mantle that has seen melt extraction maybe 5, 10 times, and this is something very important. Okay? Then came the isotopes, and for me, I like to honor here someone who's been confined to a minor role of analytical genius. I mean, it's Mitsunobu Tatsumoto here. That's for all those who knew him, okay? And as far back as 1966, Tats has realized something absolutely visionary. He measured lead isotopes. You don't care about what is in this plot, but it's this beautiful science paper. It is the isotopic composition of lead in oceanic toluites suggests that the upper mantle source region of the toluite was differentiated from an original mantle material from more than 1 billion years ago. Okay? It's not a reason. Gas couldn't tell more because it didn't have the isotopes that actually at that time it hadn't figured out the lead isotopes at Lamont, but Tats had actually, he was a postdoc with Claire Patterson and learned lead from Pat, and these guys had figured out that actually we are watching long-lived reservoirs and not some active process that we're seeing and going on in a few tens of million years. Hart came with a similar statement in 1970. This is a paper with Dan Carrig. So far, nobody has actually evoked the back arc basins, and showing that there are some major differences in strontium isotopes, okay, in between mid-ocean ridge basalts and some other basalts like Lao basins. And what you see here is something which looks, well, this is always diagram with geochemistry. No, but it takes billions of years to create that kind of difference. So if these basalts are produced at mid-ocean ridges, if they are produced at ocean islands, they come from places in the mantle that remain isolated, at least partially isolated from each other for billions of years. And that's something absolutely essential. Probably we must credit Stanhart here for really pushing this idea that the mantle was extremely heterogeneous, and actually the stroke of genius was by Hart and Schilling and Powell. This paper is absolutely fantastic. When you see, this is Wilson and Morgan deep plumes. You have Hawaii here. You have Hawaii Emperor chain here. The distance to the Kilauea that goes to here is very nice, and there are some interpretation. And the dominant interpretation is that there is some hot spots under the plate. The plate is moving on top of the hot spots. Okay, and And what you see is that if you look at isotopic data above Iceland, above mid-ocean ridges, you see this very strong step here, indicating that actually the mantle below Iceland has nothing to do, or very little to do, with the mantle below the ocean, the mid-ocean ridges. So it's actually probably, I could consider this important, but this is telling us that something from a reservoir, whatever you call it, okay, an entity that had nothing to do with the entity that produced the mid-ocean ridge. So when the Wilson-Morgan concept of deep was combined with the isotopic evidence of long-lived heterogeneity, it became clear that plate tectonics manifests that the oceanic lithosphere is the thermomechanical boundary of the upper mantle, not the lower mantle, the upper mantle. Plumes are short-lived features. They probably last something like for tens of thousands of years, but they're short-lived feature from the lower mantle burning to the upper mantle. What was the geochemistry good at? Okay, we had to understand, as it became clear from the previous talks, that we had some ideas about something was going on mid-ocean ridges. What is a ridge? Okay, we know there is magma. Okay, but the idea. So the closest analog of a mid-ocean ridge was ophiolites. You know, pillar lavas on top. Underneath you have the sheeted dye complex. And underneath you have accumulative gabbros. And there's some crystals accumulating at the bottom of a magma chamber. If you want to make it this way. This is a geology. I forgot to to quote the author here: pillar lavas and then the sheeted complex. We had a long discussion about the nature of layer 3 and things like this. There was these debates that are long gone. And from the experience of Apollo missions, this is another paper by Paul Gast here, Gast and Hubbard here. You see that these are rare earth elements here in the moon, and you see these huge europium anomaly, negative europium anomaly. That cannot be produced by magma fractionation. It means that the planet was differentiated. Okay, using that example here, this is the observation by Masuda, by the Japanese group, that there were some positive europium anomaly. It means that under the ridges, there were some magma chambers with active magmatic process, differentiation process. And that at some point, we had some accumulation, and it became clear when we looked at ophiolites. This is the PhD of my good friend Raymond Montigny in 1973 on the Vourinos under the supervision of Claude Allègre, and Kay and Seneschal here. You see that you have a positive anomalies and negative anomalies. So we have a well-structured set of rocks that we all know today, but we didn't know that back then, that they form a coherent set of petrological varieties of rocks, and a ridge is not only magma coming up, there's also a magma chamber stagnating under the ridge, and which is producing all these different rocks. Now the subduction zones. Subduction zones, the stroke of genius was by Kuno in 1966. I'm not going to explain the details of the point, but actually he pointed out that you have the silica content in basalt decreasing inland. Here you have toluites, and here you had alkali basalts. And something that people loved in these days was to plot percent K2. It looks serious. If you say distance to the trench, it doesn't look serious. But if you put depth above subduction zone, that's really serious. Okay, and you have this paper by Dickinson and Atkinson that became immensely successful. And there were some very interesting observation, again by Tatsumoto, the lead isotope variation basalts across the Japanese island result from different proportion of plate material and upper mantle. And then Armstrong and Cooper, and Armstrong was absolutely critical in this. Oceanic sediments are dragged down into the mantle, something that Harry has already formulated, mixed, but that was evidence from isotope, mixed to some degree of mantle material and partially melted from calcaline to form calcaline basalts. And then this absolutely visionary approach by Dick Armstrong, who died a number of years ago. Unfortunately, let me see if I can go back here. Essentially, that created the modern vision of mantle convection and the relationship with plate tectonics on top here. Okay, you have the plates moving here, and we drag material here, interaction with continent and with the lithosphere. The Earth, probably the major misunderstanding by Dick Armstrong was to consider the Earth a steady state, a subduction of the altered oceanic crust, including sediments and orogenic volcanism, balanced magma extraction at mid-ocean ridges. Probably not something that many people will support today. So the last point is about crustal growth. You saw in the beautiful picture of the last talk, you saw this difference between continent and ocean. The Earth is absolutely characterized by the dichotomy of between continents and abyssal plain. No other planet has that same kind of dichotomy. It is something so. And we can recognize plate tectonics. I'm a firm believer that plate tectonics is necessary for the origin of life. It is extremely important. And that dichotomy here means that the continents have to grow, have to be produced in one way or another. First, just to entertain you, there was for a while an interesting suggestion is that the Moho was actually a phase change. I mean, geophysicists always start with phase changes. You have this, you can read it very well, the identification of the more, by whom? By these two. You know, when I was a young student, Claude Allègre handed me over that paper. He knew that I could solve a first order ordinary differential equation, okay? But it gave me that paper, which is just 50 pages of solid math. You know, and they explored, Rick O'Connell and Jerry Wasserberg explored to the bitter end the consequence of the phase changes, the Moho. Unfortunately, they hadn't figured out that some people didn't like that at all, and petrologists, this is temperature and pressure. You have the eclogite, which is the high pressure equivalent of basalt, and they would consider that the suggestion by Lovering in 1958 was that actually the Moho was a transition, the phase change between basalt and eclogite. And Green and Ringwood, of course, demonstrated that it was not anything possible. Second, the growth, and the growth of continental crust. This is someone who's been also whose contribution has too often been minimized is Pat Hurley, who was a professor at MIT, and in 1962, he drew this picture of North America, and you see the ages here, and you understand everything about crustal growth. Okay, crustal growth is there, is visible, was visible in 1962. It grows laterally, essentially laterally. We create new segments. Here you recognize the Greenville, here the superior. The ages are wrong, okay? It doesn't matter. The ages are not completely precise, but we see that there is a crustal growth here. Crustal growth is in there. And it tried to putting bullets fit to good use by putting, that's a little later, by putting all the cratonic zone, and he tried to suggest that it was core. But crustal growth is something that has kept busy people for 15 years. And here is the paper, famous paper by Reimer and Schubert in 1984, showing the amount of crust from 100% to 0 to 100% of the present day volume through time. This is today, this is 4 billion years ago. And you have all these crusts. People were extremely excited by this kind of crust because it has enormous geodynamic implication. But already in Hurley's report in 1965, he was the first to demonstrate that crust was actually growing and giving some kind of numbers associated with this. Okay? And then we saw, well, we all think crustal growth. How does crust grow? Well, it's obvious. It's subduction zone. No, it's wrong. It's absolutely wrong. And you can tell that it's wrong because this is Gastill, who was a professor at San Diego State in the 50s and the 60s, and he had compiled the ages available at that time. Okay, here. Okay, it's a bit stretched here, but the ages are the same, 500, 1,000, 15. So it had compiled all the ages you could get from minerals. Okay, any method, at that time it would do. Okay, at that time any method would do, potassium, argon, rubidium, strontium, and micas and things like this. But this is actually quite spectacular. You have here the superior event here. You have the superior event here, you have the North Atlantic Craton here, you have the Grenville. Look how much it has changed over 50 years. This is almost the same, okay? And we haven't learned our lesson from this. Okay, some people are trying to argue that there is selective preservation of sediments, and this is not the fact that it's an episodic phenomenon. Crustal growth is not an episodic phenomenon. It is an episodic phenomenon because what we understand is that we were removing preferential this, we would find the counterpart in detrital sediment, for instance, which we never do. Okay, we have an episodic crustal growth. So, and we know that plate tectonics, as far as I understand it, is plus or minus 30% some kind of continuous project. Okay, it's a process. Sorry, it's a continuous process, and you see that how can you make crust grow discontinuously out of a continuous process? That is the problem. And the solution, of course, is plume. And where do plume come from? They come from the deep mantle. I don't know if they come from the 660 or if they come from anywhere else. It doesn't really matter. But essentially, if plumes are the super plumes are the discontinuous process we need to make the crust, this is something important. And it's not the subduction zone. Subduction zone, what is their job? It's garbage collection. Whatever is actually drifting on top of the mantle gets one day or another overthrown or collides with the existing continents. But this is not the founding act of crustal growth. Okay. So, in a sense, deep mantle plumes are the continent makers, and this is kind of. So, what is left of the whole thing? Geochemistry is process-oriented. It's something we're not discovering anything new here. The good thing is about radiogenic isotopes because it has the dimension of time. Geochemists can look back. You know, when you look at the Earth today, you look at the Earth over the last, especially the ocean, over the last 100 million years or so, or 200 million years. Geochemistry can go back to 3.5 or sometimes 4 billion years. Okay, this is radiogenic tracers are the most powerful, the billion-year timescale, whereas the mean age of the ocean is something 65. The oldest piece of oceanic crust is 200 million years. And geochemistry helped resolve some conundrums created by either petrology or seismology. The Mo is more than a phase change, and so is the 660-kilometer transition zone. The continental crust, the upper mantle, and the lower mantle are geochemically distinct geodynamic entities and have remained, so far, most of the Earth history. In a sense, what I'm saying is that if you make a phase change, like in many cases geophysicists like to make it, Okay, it means implicitly it means that the mantle is homogeneous. When you make the discontinuity a boundary between different entities, like geochemists like to do that in the 90s or even the year 2000, layered mantle convection, then we have a problem. We have a different chemistry. We actually have a combination of both. Phase change actually acts to solidify the boundary between geochemical reservoirs or between geological entities. They're not impermeable, but we have this combination of things, and it took us time to figure it out. And as I said earlier on, geochemistry is Bloom's best friend. If you want to see a way of explaining Iceland and the Reykjavik ridges without using the deep mantle, or some sort of very, very different reservoirs and in the layered earth, we're going to be in trouble. So Tuzo Wilson's and Jason Morgan's plumes are extremely strongly supported by geochemistry. So, if geochemists were not there attending plate geochemistry, is also that they have their hands busy and their plate full with another task. It was exactly the time plate tectonics coincide with the Apollo missions, and there was a competition between the different things. And we all like to talk to God, so we had our head in the stars rather than looking at our feet, and that's what the situation was about. Thank you very much.